So our topic is file I/O using system calls. As an introduction, let's first quickly review the role of system call. System calls provide programming interfaces to the services of the operating system. At the very top we have the users. Users are running all this application software, Firefox, Chrome, Facebook, C program, etc. Then all this application software is running in this hardware, which consists of CPU, RAM, monitor, hard drive, etc. Now, whenever we have to access this hard drive in a modern operating system, we cannot do it directly. We have to pass through the operating system to access this hardware in privileged mode. This means our application software has only unprivileged access in user mode, and whenever we have to do anything critical in kernel mode, we have to go for privileged access. Now, if we are writing a C program, if we have to avail of this services provided by the operating system, we'll have to go through this set of system calls. Okay, and these system calls are programming interfaces that enable our software to actually access hardware in kernel mode. Most of the times we don't think about system calls. So the question is, if system calls are so important, why are they not visible to us? And the answer is that high level languages provide function calls that indirectly invoke system calls. So if we make a function call, some function call, say for example if we want to access a file, if we fopen a file, then internally that function call makes an access to the system call. That's why you are not able to see it. The system calls are very important, but it's invisible to us because they are hidden by the higher level programming languages like C and C++. So we are going to write an application software which actually does file I/O, but it does not use C. We want to write an executable, but this executable, what we are saying, should not use the standard I/O library. Why? Because we know that if I have to do anything with the operating system, there is no requirement that we have to use C. Okay, so what are we proposing today? We're going to do the same file I/O application. We'll open a file, we'll write to a file, we'll close a file, etc. But no C, no function call. We are going to directly use the system calls. For example, here we can use the open system call, close system call, exit system call. What is our target today? Our target is to write an application software, a program that does not use standard C library. Instead, what it does, it directly, this a.out will directly invoke these system calls. So it will do an open. The moment we do an open, we know that it will go and create a file here, abcd.txt. So the moment we do an open system call, it will create a text file called abcd.txt. Okay, then we can go ahead and close that file like this. And the moment we close this file, what is going to happen? We have created an abcd.txt, but since we have written nothing, this abcd.txt in our case will be a 0 length file. Okay, and then finally, in order to terminate our program, we are going to make a exit system call. We want to create a file named fileio.asm. And what is this file? This file is a file that performs file I/O directly. Now exit system call is easy. So let's say section.text global start move eax1 move ebx3 int 0x80 make exit system call. So what we have to do in order to make this exit system call, first we will move eax to 1, ebx to 3, and then we give an interrupt. And the moment that happens, then exit system call is created. So in order to perform this exit system call, we have to first fill up the A register with the corresponding syscall number. So we from the syscall table, we have just seen that exit has a syscall number of 1. So we have just put 1. EBX is just the status, and after that status we have to give an interrupt 0x80. So this is a program that we have to run. So let's run this program now. So the first is that we have to run an assembler. The moment we run this nasm command over file.io.asm, what is the output generated? The output now that is generated will be file.io.o, the object file. Now this object file will be given to the loader to create the executable. So let's do this. Load -m elf i386, then file.io.o. And the moment we do this, we can see that an a.out has been created. Now we have to just run a.out like we did earlier. And when we do an echo, we can see that the exit status that has been returned is 3, just like in our program. Now in order to do this open system call, what is the requirement? First, we have to find the syscall number for open. Say AU syscall i386 open. What is the number? Syscall number 5. So let's write it in our figure here. So our syscall number here, the syscall number here is 5. So our target is to invoke the open syscall. So these are all the registers of the CPU. We have to first fill up this EAX with 5. What is 5? 5 is the syscall number for open. Now, how many arguments are there for the open system call? Man to open. So what is the first argument? The first argument should be path name. What is the second argument? The second argument should be flag. And what is the third argument? The third argument should be mode. So EAX is the syscall number. This is the first argument. And this will be path name. What is the second argument? The second argument is flags. And what is the third argument? Mode. EBX mein to the path name is given, no? So you have to just fix the path name. And what is the path name? Path name is abcd.txt. So in the second argument, we have to provide flags, and in the third argument, we have to provide mode. Now we don't know the value of all these. Okay. So in order to find the values of these two second and third arguments, rather than we figuring out manually, we can cheat by running the strace command. And what does strace do? Strace gives us the system trace, the arguments of all the system calls that we make. So first we run strace.a.out. Then we look at this flags argument and the mode argument from the strace.out. Remember that the C program that we earlier wrote, remember this, where we use this fopen, fwrite, fclose, etc. No, we just want to look at this output. So now let's run strace on this a.out. And what are the arguments? This argument is abcd.text, the first argument. What is the second argument? O read write, O create, O append. That's the second argument. And what's the third argument? 0666. 0666. Now what is this value? O read write, we have no idea what this is. So you can just copy paste, just print it. Second argument to open syscall is this is hexadecimal, and just print this guy. cc file access.c and run it. What's the value? Hexadecimal 442. Now we can go and put this value hexadecimal 442. Now let's look at this open system call once again. Man to open. It returns an integer. So there is a return value of this open. So by convention, the return value will be stored in a register, EAX register. The moment interrupt comes, CPU will know, oh, open system call is being executed. Then what will it do? It will return the file descriptor. That is, every file has some descriptor. That descriptor will be returned to this EAX register. So what will the EAX register contain now? After the system call, it will contain the file descriptor. Now, ye file descriptor is critical. We cannot lose it. We cannot lose this file descriptor because we have to do operations on it. So this file descriptor is very important. Therefore, just to make it doubly triply sure, we are going to save this file descriptor in EDX. Now let's write this code here. Yeah. First, make open system call. Let's look at the figure. Move EAX file, move EAX file. Move EBX file name, section dot data, file name db abcd.txt 0. This is the file name. Okay, so the second argument is over. What is the third argument?
0x442.
Okay. Move 0 ECX 0x442. And EDX, what should be the value?
066.
Okay. Move EDX 0666. Then we do an interrupt 0x80. So now the call is ready. Now where will be the return value? Save the return value of open system call. So let's move to EDX the value of EAX. So what are we going to do? EAX with the return value is there, no? We save it to EDX. Now let's go for the third one, the last one. Third one is what? Third one is the close system call. And in order to execute any system call, you want to know the syscall number. So what is the syscall number for close? The syscall number for close is 6. Close system call. Okay. And in close system call, what are the requirements? You need only 2 registers, I think. EAX and EBX. In EAX, what do you have to fill up? You have to fill up the syscall number. 6. क्यों 6? यहाँ पे ना close का 6 है. Now how many arguments do you have for close system call? We'll say man to close. How many arguments are there? एक ही argument. वो argument कौन सा है? वो है file descriptor. Open system call returns file descriptor in EAX. और हम लोगों ने क्या किया है? ये रिटर्न जो फाइल डिस्क्रिप्टर है इसको हम लोगों ने कहाँ सेव किया है? हम लोगों ने EDX में हम लोगों ने सेव किया है. So here we can just put the value of EDX. And what is EDX here? Why are you using EDX? Because EDX contains file descriptor. After open system call, now we are going to make close system call. And in order to do the close system call, what is the requirement? EAX में the value should be 6. Move EAX 6. Then what should be the value in EBX? It should be EDX. Move EBX EDX. Why EDX? Because देखिए line number 18 में we have saved the return value, the file descriptor. We have saved the return value of the open system call, which is the file descriptor. Once it is done, then you can go interrupt 0x80. Is this okay? So this picture, the picture that we have just drawn, this picture is practically implemented in this file. Let's go to the code directory. In code directory we have just file io.asm, just one file. Okay, it has just one file, this file. Now let's first pass it through the assembler. File io.asm. The moment we execute it, an object file will be created. Enter. See, this object file has been created. We had this file io.asm as the assembly language program. An object file has been created. Once that object file is created, we already know it has to be given to the linker, the system linker, and it is ld-f elf i386 file io.io. This is what we have to do. The moment this happens, we'll have an arrow dot. Now when we execute this arrow dot, now a 0 length file named abcd.txt should be created. You can delete it, and if you run it again the right side में ध्यान से देखिए, enter, and a file will be created. So we have just seen that you don't really require C programming, C++ or Java or whatever programming. You don't require any of the programming languages to actually create and manipulate files. What is the target? What is the target? Target is that we want to perform file IO operations but without the use of any high level language. Basically, we want to perform IO operations based on system calls only. And what are system calls? System calls are those interfaces that are provided by the operating system to access its services. In particular, we are interested in 3 system calls: open system call to create a file, close system call to close that given file, and exit system call to actually exit the program. Now, whenever we make this open, close, and exit system calls, we should be able to create in this hard disk a file called abcd.txt, which is a 0 length file. So our requirement is that we want to access the hard drive through the operating system and create a 0 length file named abcd.txt. In order to do this, we have to execute 3 system calls one after another: open system call, close system call, and exit system call. Whenever we have to execute any of the system calls, we have to find the syscall numbers, and to find the syscall number is very easy. You just use the AU syscall to actually figure out what syscall number for each system call is. Arguments also can be found likewise from the man pages. And once we have found the arguments and set up the registers correctly, like if we have to say execute the open system call, then EAX is 5 because 5 is open, syscall number is open. Second is path name, so we put it here. Third is some flags that we'll talk about in a later date, and the fourth one is the mode of the file. We set all of this up and then issue a software interrupt. The moment a software interrupt is issued, it first creates that file and it also returns the file descriptor in another register, the A register. Now, just for safety purposes, we save this A register somewhere safe. Here we have decided to arbitrarily save this file descriptor in the register, in the integer register edx. Okay, and after repeatedly executing all these system calls one after another, we are able to get a 0 length file without using any high level language.